I think we can start. It is always a great pleasure to open RISM School. Welcome to everybody and each one of you. This is the 7th edition, is the major event of RISM, and the first one was in 2009 on the occasion of the 150 years of the Riemann conjecture, directed by Bombieri, the second one by Nirem, the third one by Quarteroni, and then Donaghi, Ekeland, Martin Eirer on the occasion of Giuseppe da Prato birthday. I always call Beppe because is usually called Beppe. And I'm very grateful to Luigi for accepting to direct this 7th edition of the RISM School. And the topic is very challenging, is mainstream research. So, and the novelty of this year is that we have a population of very young researchers. So I'm very happy also to see so many young coming from all over the world. We have from China, from Europe, from US, and I wish you a pleasant stay here in Varese, in Villa Töplitz, at RISM, and to enjoy a fruitful workshop during this week. So thank you very much. I want to thank in particular Maria Colombo for the organization, Elia Bruet, and they did all the job, actually. So thank you very much. Thank you all.
Okay, so let me just add a few words to Daniele. I have also to thank Elia and Maria, who really did a lot of job in the organization. When we started to think about this event, we really wanted to have something related to new developments, exciting developments, and to get as much as possible young people involved. So I think that we met this goal, and I hope you will enjoy the school. I am personally also very interested because I always heard about all these new results, but I never worked really on them. So it will be also a pleasure for me to attend this school, and let's have a nice time here. Thank you.
So let's start with the first speaker, Dallas Albritton from Institute for Advanced Study, Princeton, and he is giving a mini course on self-similarity, singularity, and non-uniqueness in partial differential equations of fluid dynamics. Please.
Okay. Thank you very much. Very happy to be here. Thank you to the organizers. Okay, if you can't see, please let me know. I'll try to write bigger. So yeah, as I said, I'm Dallas, and feel free to ask me questions between the talks. So there are going to be typed lecture notes for this, but they're not going to be done by the end of the week. So maybe within a couple or a few weeks or something, they should be on my website. But okay, but don't set your expectations too high for the emergence of the lecture notes. Okay, so the lectures are going to be they're mostly going to be about non-uniqueness, but I want to explain a bit about self-similarity in general. And in the context of PDEs. And self-similarity, I mean, it pops up in a lot of places. It pops up in singularity formation problems, problems of continuation past singularities, so, I mean, including non-uniqueness problems, which we'll focus on, and also in long-time behavior of solutions of PDEs. So today we're going to actually focus on, okay, so you also have to be a little patient as I figure out all right. Yes, so today we'll focus on self-similar singularity formation. Okay. But what is self-similarity? Okay, I mean, there are many ways to introduce self-similarity. In the context of PDEs, self-similarity refers to when solutions of PDEs live across many different scales. But when you renormalize to unit scale, the solutions look coherent. There's like some coherent object or family of objects which are driving the evolution. So I want to talk about start by talking about Navier-Stokes. Okay. So I'm not really going to introduce the equations in great detail. I'll assume some familiarity. Okay, but here are the Navier-Stokes equations. And so the equations are endowed with, well, let's do a little dimensional analysis. So use a velocity field. Dimensionally is dimensions of length over time. Okay, x is dimensions of length, t is dimensions of time. And the pressure, okay, the pressure is a little funny because the pressure isn't really pressure. The pressure is really pressure divided by density, which is typically, we don't talk about that so much, but its units are length squared over time squared. And I want to put the parameter nu back in here. Okay, so there's a parameter in here, nu. All right. So nu is the kinematic viscosity, and its dimensions are length squared over time. So in water at room temperature, this nu is like 10 to the minus 6 meters squared per second. It's pretty small. So this viscosity parameter, okay, it depends on the fluid and temperature and various things. We consider it to be a constant, and it's a dimensional constant, which lets you always relate length squares in time, just like we use speed of light to relate time and distance. Right, one light year is actually a distance traveled by light in 1 year. So whenever you have a dimensional constant like this, you can use it to relate different sets of units. So if we use the viscosity to relate length squared in time, then actually u, I mean, so if we basically consider this to be like 1, then actually u has dimensions like, all right, so if this is like 1, all right, then u actually is dimensionally like length inverse, because length is like time squared. So time is like length squared. The pressure is like length to the minus 2. All right, so in this dimension counting, okay, whenever you have an equation which is dimensionally correct, it comes endowed with a scaling symmetry. So for Navier-Stokes, the scaling symmetry is simply this. Okay, I mean, here, let me put Navier-Stokes back. I want to use the evidenziatore. Okay, so for Navier-Stokes, so let's just get Navier-Stokes up here again. So if you have a solution to the Navier-Stokes equations, then you can rescale it by scaling factor lambda. Here's the scaling. You can also rescale the pressure. Well, you also should rescale the pressure. And OK, so if you're given a solution of Navier-Stokes, you can produce another solution by rescaling. And so in 1934, Jean Leray, who wrote the first real PDE paper on the Navier-Stokes equations, okay, maybe. In any case, he wrote one of the famous papers. He proposed and ansatz for finite time blow up for the Navier-Stokes equations. All right, we recognize that that's an important problem. So Leray proposed to look for solutions of the Navier-Stokes equations which live for all negative times, they live for all backward times, and at time 0 they concentrate and blow up. So we're considering that he was talking about solutions which live in the whole space and in backward time, so-called ancient solutions. And he asked whether such solutions exist which are invariant under that scaling symmetry. Okay, so in other words, U equals U lambda. Okay, so we do a simple computation. We write U of xt. We just write out what this says. This is lambda U, lambda x, lambda squared t. And so if we pick the choice that lambda, so if we pick the choice that lambda equals square root of minus t, probably 1 over square root of minus t. And you plug in, then you get this. 1 over square root minus t, u, x over square root minus t, negative 1. So in other words, in this setting, if you have these scaling invariant solutions, also called self-similar solutions, then they're determined entirely by what they're doing at time negative 1. So we give that object a name, all right? So we call this variable xi. So we call that our self-similarity spatial variable, our dimensionless spatial variable, whatever. And then this object here, the profile at time t equals 1, we call that capital U of xi. So if you know capital U, you know what the solution is doing for all times, for all backward times. Okay, and I have a little bit of room on the board to, maybe I'll draw a picture on the next board. I have a little bit of room to compute some norms. Okay, so if capital U is a bounded function and is not identically 0, then we can easily compute the L infinity norm of this little u, all right? Because this thing here is capital U simply being rescaled. It's being multiplied by 1 over root t, so the L infinity norm will grow like 1 over root negative t. Okay, so it'll have a singularity. So more generally, we can compute the behavior of all LP norms. So we compute. So this is so we bring the root negative t factor out front. And then this is capital U evaluated at dot multiplied by minus t to the 1/2 to the minus 1/2 LP. So this number should be like minus t to the minus 1/2, that's from out front, plus d over 2p. Okay. D is the spatial dimension. So d is 3, say. So we see from this that if p is greater than 3, then okay, d is 3. Okay, so if p is greater than 3, then this norm will explode in finite time. And if p is less than 3, then this norm actually goes to 0. So that's a bit weird. And so, but this calculation only makes sense if capital U belongs to the LP space. Okay, so in other words, if you have this self-similar blowup, you don't actually expect the solution to be finite energy, because then it'll vanish identically at the blowup time, and that's no good. So what you really expect is you really expect U to be big O of 1 over C. Then this calculation will make sense for all p greater than 3. When p is exactly equal to 3, it will not make sense, because this doesn't belong. A profile like this will not belong to L3. It'll belong to weak L3, and the weak L3 norm stays order 1. And functions like 1 over x. I mean, basically the crucial point is that functions like 1 over x are invariant under the scaling symmetry. So this is what one actually expects. So do these solutions really exist? Let's find out. So let me just write the ansatz again. So you plug this into the equation. Let's start by plugging into the time derivative. So dtu. We're going to have the time derivative. First of all, it hits the 1 over root negative t. So you're going to have minus 1/2 minus t to the minus 3/2. But OK, we also need to multiply by minus 1. So let me just change this into a plus. And then we'll have capital U. When the time derivative comes inside, hits capital U instead, then we'll have, so I bring this factor from out front. I need to take this gradient, so it's going to be gradient with respect to C of U dotted with x, nope, all right, not a problem. So dotted with x, and then minus t to the minus 3/2, again multiplied by minus 1. 1/2 plus. Okay. All right, so we could go ahead and also do this computation with all the other factors. What you'll find is you always have this factor popping out, minus t to the minus 3/2. What about this one? This one has minus t to the 1/2 times minus t to the minus 3/2, so that seems like there's an excess. But you combine this with x to make c. So these two, all right, they make c. So if you do this with every term in the Navier-Stokes equations, and then you divide through by the excess factor, you'll simply get 1/2 u plus 1/2 c dot grad cu minus Laplace u plus u dot grad u. All right, you have to plug in the rescaling for p as well. And OK, so if you can solve these equations, then you can win $1 million. Because these, if you find a non-trivial solution of these equations, then it'll give finite time blowup for Navier-Stokes. OK, in the infinite energy class, but you can probably play some game where you cut it off and get finite energy solutions. So these are the equations for the profile capital U of a backward self-similar blowup. And it's an elliptic equation. And there's this theorem. So there are various authors. Let me just attribute it to Taipeng Tsai. That's Hyunju Kwan's advisor, 1998 in ARMA. Okay, so if the profile U is bounded above like 1 over C and solves, let me give this a name, star, then U, that's 1 extra, then U is identically 0. So in other words, there are no within this very reasonable class, and people have since extended the classes, and they've looked at approximately self-similar blowups and things like that. But within this very reasonable class of blowup profiles, there's no backward self-similar blowup. So I'm not going, I mean, there's no way I can go over the proof, but let me just say that, let me say something about what goes into this. So basically, for solutions of steady Navier-Stokes, for solutions of, I'm not going to go on a new board. For solutions of steady Navier-Stokes, there's a quantity called Bernoulli pressure or head pressure or total pressure or something like that. And that quantity is U squared over 2 plus little p. That's for solutions of steady Navier-Stokes. And this quantity actually satisfies, I mean, there's actually a maximum principle for this. Basically, for solutions of steady Navier-Stokes, you have this equals minus, so this quantity is actually a subsolution. And there might be a 2 here. When the notes come out, we'll know. This can be proved this can be used to prove various Liouville theorems. There's a variant of this quantity which also works for the backward Leray equations. And it can be used to prove this kind of Liouville theorem. Okay, questions about this? All right. So let's just say that you're not. Okay, when you're Jean Leray and you invented this ansatz and you're not exactly correct. Okay, but maybe you made some error and you actually want to allow not really a truly self-similar profile, but a self-similar profile that, you know, maybe it kind of lives at the scaling, but it kind of oscillates around some equilibrium in the scaling. Okay, so you want to put time dependence back in the problem. In which case, you want to leave time in this ansatz. Okay. Now, when you compute the time derivative, there'll be one more term because there's going to simply be dt of capital U. So, in addition to these terms, you're going to have plus minus t to the minus 1/2 dt capital U, like this. And when you multiply the equations through, you'll see that what you're left with is this equation, but you're left with this equation, but it's going to be multiplied by t. You'll have this additional term that's t dt capital U plus all this stuff. Okay. And this leading term defines a very odd kind of evolution. And so we don't like that. We don't like this t dt u. We'd rather have an autonomous equation. So you don't put t here. What you put instead is log 1 over minus t. Or if you like, minus log of minus t. Then that term, so we give that a name. Just like we call this thing c, we call this log tau, this logarithmic time. And then this term here, becomes okay, this term here
It's the boundary insensitivity.
yeah, it's the all right. Yeah. So don't touch the boundary layer. Okay. So yeah. Okay, this is better. Except now I'm using blue. This is your equation. D tau u plus all that stuff. Okay, so now this is a time-dependent problem. And then you don't have this theorem. And to the best of our knowledge, you could have blowups that live basically at this scaling, where capital U is order 1. For example, you could have a blowup, to the best of our knowledge, you could have a blowup, capital U, which is time periodic in these variables. So the meaning of that in physical variables is that the blowup would be discretely self-similar. It's not invariant under all rescalings, but invariant under, say, a subgroup of rescalings. And yeah, in these variables, it looks time periodic. For example, in principle, you could have a solution which in these variables is rotating with constant speed. And if you undid the rotation, it might look steady. So that would be a kind of rotationally self-similar blowup. All of that is unknown, seems to be open. And there's some further discussion. If you look online, Vladimir Sverok has 3 lectures on YouTube, which he gave at the Fields Institute during COVID. But he's a very good COVID lecturer, so the lectures are very beautiful. And he has some discussion of this idea, and also some conjectures about how it should arise in some other equations. And I think it's worth taking a look at. So if you look at, if you search Vladimir Sverok, Fields Institute, suggestions from computation or something, then it comes up. All right. So these variables, xi and tau, we're calling them similarity variables, and we're going to use them every day until Thursday. Questions about this? Cool.
Sorry.
Yes.
So you tau, you impose some kind of, let's say, capital U is periodic in tau or something like that.
Yeah, if you had something like that, then that would be a discretely self-similar blowup,
Okay, so
and that would also net you $1 million.
So okay, for the viewers, now I asked if putting the tau, we need to have some kind of similarity, right? We need to impose some conditions on capital U, for example, periodicity or something like that.
You mean like boundary conditions, or?
No. I mean just to.
So this is a general change of variables, which just works for any vector field. And so far, when you make this change of variables, the way we've done here, so far you've done nothing. All you've done is predict that the dynamics of the problem occur at a certain length scale. All you've done is predict that the correct dynamics of the problem occur at length scale minus t to the 1/2. And so what you've done here is say, the right way to look at this problem, if things are concentrating at that length scale, is to renormalize and blow that length scale up to length 1. So we're taking, I should have drawn this earlier, but we'll draw it now. So the picture is that these similarity variables, so I have axes like xi and tau, and let's say I draw like 2 lines in the similarity variables. In my solution, it basically looks like it's like order 1 in these variables. It lives at unit scales and it's order 1. And then you map this onto the similarity transformation. And so, by the way, crucially, tau goes all the way to plus infinity. So, your problem actually, the singularity time t equals 0 goes all the way to tau equals plus infinity. So tau goes to plus infinity. And here's if your solution is living here, x in R3, and then here's time going to minus infinity here. These 2 lines in similarity variables get mapped to basically this parabola. And you draw some more lines here, and they get mapped to this parabola. And your solution, in your guess, basically, if you had a backward self-similar solution, which typing psi showed do not exist, then basically, in this picture, they look like at time minus 1, they look like some like some bump which decays like 1 over x. But then when you get to the blow-up time, they just look like they're big O of 1 over x, like that. So this bump, it's like you're zooming out on it, and it's being compressed into the origin, like that. So, but in this picture before the transformation, everything just looks like order 1. There's like a bump here. It's like the same bump here, roughly the same. So it's this idea of if you can correctly predict the length scales at which singularity things should be concentrating, then you can blow it up, renormalize it, and this lets you study like smooth dynamical problems instead of studying problems which are rough. All right, that's kind of a long-winded answer, but is that helpful?
Yeah.
It would be good to have like 2 boards. All right. So it's kind of funny to say, oh, I'm going to talk about self-similar singularity formation, and then just say, oh, and it doesn't happen. So let's talk about, I want to talk about burgers. I want to talk about some, I want to talk about examples for which we do know that there's self-similar singularity formation. So, the kind of classical examples are semilinear heat equations and Burger's equation. And the literature on semilinear heat equations is really vast. By the way, that transformation with the tau equals, minus log minus t, that was introduced in the context of semilinear heat equations by Giga and Cohn in like the late 70s, early 80s. Let's just talk about Burger's equation. So Burger's equation doesn't have a viscosity parameter. Remember we said that for Navier-Stokes, you have length and time, and viscosity is going to relate length and time. So you do these rescalings, which always preserve the viscosity. This equation has no viscosity, so you can rescale length and time separately. So U, and we think to ourselves, U is dimensionally like a velocity field. And so the scaling transformation is a 2-parameter transformation. So U of lambda mu function of x and t is this rescaling, lambda x mu t. So if you have a solution of Burgers, and you make this rescaling, where, in other words, where you rescale length and time independently, you get another solution of Burgers. Now, if you want to talk about self-similar solutions, then you need to, you don't need to, but you usually pick a one-parameter subgroup of this two-parameter scaling group. So you normally say, I'm going to identify length to the alpha and time. Time is going to be like length to the alpha. And then you get a reduced scaling symmetry, where you always pick, I'm sure I'm going to mess it up, but I mean, you always pick mu to the alpha, lambda to the alpha is mu. And then you ask the same question. Now, are there solutions which live for all, ancient solutions which live for all negative times, and which blow up at time t equals 1, and which are invariant under that scaling symmetry? So this leads you to define variables. Xi is x over minus t to the 1 over alpha. That should be dimensionless. And again, we use tau is log 1 over minus t. And your invariant solutions should have this form. U of xt is minus t to the 1 over alpha minus 1, capital U of xi and tau. That's your ansatz. And OK, if they're invariant, then there should be no tau dependence. So like this. By the way, how did I come up with this factor in front? It's because U is if U is a velocity field, then it has dimensions length over time. So my factor in front should represent that. And minus t to the 1 over alpha, that's length. And this minus 1 is 1 over time. So this is length over time. And solutions of the Burgers equation, which have this form, must satisfy this ODE. So, OK, the time derivative comes and it hits this factor in front. That's what produces this term. The time derivative comes inside and hits xi. That's what produces this term. So that explains these numbers. So now you want to solve this ODE. Let's do that on the next slide. Minus 1 over alpha minus 1 u plus 1 over alpha xi u. OK, so you want to solve this ODE. And here's a good way to do it. You can do it by inverting the dependence of u on xi. So let me say xi is xi of capital U. Let's just say I can do that. So then u is the new independent variable. And this is going to be 1 over alpha xi by inverse function theorem or whatever. This is 1 over xi prime plus u 1 over xi prime. So you multiply through by xi prime. And now this is actually linear in xi, and it's inhomogeneous. So you should start by finding a particular solution. then solving the inhomogeneous equation, and that should give you a general solution. Although it's a bit funny because when u is 0, this derivative term formally goes away, so all right. So a particular solution will be C is minus u. That way, these 1 over alpha terms, unless I'm off by a sign, which it looks like I could be. It looks like I'm. Oh, no, it's good. It's good. Yeah. Yeah. OK, this is a particular solution. And then the solution to the inhomogeneous problem. So solution to the inhomogeneous problem will be something like C is minus Cu to the minus 1 over, I'll write it like this. One over 1 minus alpha. OK, so the full solution is like minus u minus some constant c, u 1 over 1 minus alpha. And if you want your solutions to be smooth, then you want this to be an odd integer. So for smoothness, you want that 1 over 1 minus alpha is 2k plus 1, where k is an integer in the American convention of excluding 0. So for example, this might be 3. And if this is 3, this is actually explicitly solvable by Cardano's formula. But that's not necessarily the best way to look at the problem. By the way, this C is kind of inconsequential. That C encodes the fact that the equation has a spatial scaling invariance. So if you rescale a little bit in space, then you get another one of these self-similar blowups. So you might as well say that C is 1. All right, so a few observations. So the solution will be smooth. And in fact, the solution in this case of 3 is going to be like 1 over c to the 1/3 with some prefactor as c goes to infinity. So a more precise statement is that Burgers has a countable family of self-similar blowups with smooth blowup profile. And their growth at infinity is like c to the 1/3, 1/5, 1/7, 1/9, etc. So this is an explicit computation you can do. You can go farther. You can look at the eigenvalue equation for the linearized operator around these profiles. And it's actually solvable by similar methods. And a really good place to learn about this stuff, and just self-similarity in general, is a book by Eggers and Fontelos. And it's an applied math book, okay? There are not really theorems in there. So there's a book, but there's also an article in Non-Linearity. So there's a book, and there's also a survey in Non-Linearity. And again, it's applied math, so there's just a bunch of formal stuff about self-similar solutions that they've observed and done numerics on, and a lot of it's waiting to be understood in rigorous terms. But anyways, these are examples that are explained there.
One more or less.
I mean, you'll find it. Yeah, it's, yeah. So, okay, I just want to glean a couple more things from, from this. So, first of all, I want to know where the solution lives at the first time that regularity is lost. So when a shock forms, the solution isn't instantly discontinuous. The discontinuity, first the solution loses smoothness, and then the discontinuity opens up in time. So the picture is something like, okay, you're running this, and then at some point there's this cusp at some time, and then, okay, and then the solution, the shock is opening up, it's developing. So the first time where singularity is lost, that's called the pre-shock time. Or I mean that profile is called the pre-shock. And let's say you want to use these self-similar solutions to kind of predict what regularity the solution should live in at the pre-shock. All right, so we're going to compute U in this homogeneous Holder class. Because remember, I said that the solution grows like c to the 1/3 at infinity. So if you apply 1/3 of a derivative, you expect something that's essentially bounded. So this should be finite, and is. And now we compute. So if you work out what the exponent should be, in the case that everything was with this parameter 1/3, it's like this. On the outside, you have minus t to the 1/2, no negative, just 1/2. And on the inside, you have x divided by minus t to the 3/2. So in this case, alpha is 2/3. OK, so this should be taking 1/3 of a derivative through here. You should get minus t to the minus 3/2 times 1/3. And then you should just get the norm, c dot 1/3 norm of capital U. And so this thing is order 1. So at the pre-shock time, if you were to blow up this picture in similarity variables, you would see a self-similar one of these self-similar solutions. And the only stable one is the c 1/3 blow up. The only stable smooth one is this c 1/3 profile. And at the pre-shock time, you should exactly have a c 1/3 cusp. Now, you can also enter situations where you get a c 1/5 cusp, c 1/7 cusp. And there are also, if you start with non-smooth data, there are also ways to get numbers which aren't those values. And OK, and there are papers about this, also for compressible Euler. But the only stable, smooth, stable formation scenario is the c 1/3 one. OK, so if you want to learn more about this, I mean, you should check out the book of Eggers and Fontellos. But you can also look at the papers that are being written by Vicol and Scholar, Buckmaster, and also their group. And they're using this stuff in much more complicated scenarios for blowups in compressible Euler and multi-D all these things. So I'm at the 50. Maybe there's I'm going to say one more thing. So
Dallas,
yes,
the block size.
yeah.
The coffee break is at 11, so if you need more time.
Coffee breaks at 11.
Yeah.
Okay.
So there's plenty of time. So.
I see. Okay, let me, I don't want to wear everyone out too much, but I want to say something about what happens when you add viscosity back to these blow-ups, because I think this is a useful way to think. Oh yeah, by the way, these kind of blow-ups, where you have this, these kind of blow-ups, where the relationship between the exponents, where the relationship between the exponents is not clear a priori, is not obvious, and really needs to be, extracted by looking at which profiles exist. Those kind of self-similar blowups, basically there's an old name for this kind of thing. It's called self-similarity of second kind. I don't know who invented that. I know Barenblatt uses that kind of terminology. For the Navier-Stokes blowup that Leray hypothesized, that's self-similarity of the first kind. There's only, if you use the viscosity, then there's only a one-parameter scaling symmetry, and there's basically only one pair of exponents which is admissible under that. So this is self-similarity of the second kind.
What would be the first kind for burgers?
Burgers, there does not seem to be a first kind for burgers because you just can't predict the relationship kind of a priori. Yeah. And indeed, there's the whole family. So, yeah. All right. So I want to say something about viscous regularization. So let's say we study instead this equation. Either on the torus or on the whole real line. And then this operator makes sense. So on the Fourier side, that's multiplication by k to the s. So Fourier transform of dx s u is maybe up to a constant, k to the s Fourier transform of u. So obviously this is, really well studied. And this equation, it has a maximum principle, at least when s is less than 2. So s less than 2, less than or equal to 2, you have a maximum principle. When s equals 2, this is standard viscous burgers, which is exactly solvable by Kohl-Hopf transformation. But in general, you may want to study what happens under fractional dissipation. And so the L infinity norm, L infinity, a priori, you have control on L infinity. And when s is greater than 0, when s is greater than 1, if you know the solutions in L infinity, that's enough to bootstrap the solution to smoothness. L infinity implies smooth, more or less by kind of standard bootstrapping. When s is 1, L infinity also implies smooth. Or there's another way to look at it, which is that smoothness is propagated. Or C infinity is propagated. Those are two different things. That's much less trivial. That's basically work of. On the one hand, Caffarelli and Vasseur. On the other hand, so this is like Caffarelli Vasseur, but it's also, I'm just going to say Kislev et al. Basically, around 2006 to 2013, this critical case was very heavily researched. And in this case, the L infinity norm is invariant under the natural scaling symmetry. Scaling symmetry of the equations. And this is really a critical case. So what happens when S is between 0 and 1? So you expect finite time blow up, but what would that look like? So you expect finite time singularity, but what would that look like? So now we're going to use what we learned about self-similar singularity formation to make this prediction and also tell you what they should look like. And okay, the explicit description that I'm going to talk about is work of Sungjin Oh and Federico Pasqualotto. With maybe more L's? No more L's, of course not. Okay, so in maybe, this goes back earlier as well, but the explicit description is by Oh and Pasqualotto. So let's give it a try. So let's say that you rewrite the viscous Burgers plus nu dx s u. Let's say you write this in similarity variables. So again, I'm going to write u is minus t to the 1 over alpha minus 1, capital U, x over minus t to the 1 over alpha, minus log minus t. And I'm going to plug in. So all the terms that we had previously, they get this perfect factor popping out. That's minus t to 1 over alpha minus 2. OK, then the rest of the equation, I copy. So what happens to the viscous term? So this let's just compute together. So we compute together. So I have the new factor. I'm going to apply S derivatives to this thing. So I should have, in addition to this factor out front, which is 1 over alpha minus 1, I should have S copies of this factor popping out. So I should have minus S over alpha. And then I should have dxs capital U. But it's not x anymore. It's c. With respect to the first variable, dc. All right, and then I'm going to use that e to the minus tau equals minus t. So remember, t is negative. So this is OK. Remember, that's positive. So this factor here is really e to the tau s over alpha minus 1. Now, if this exponent is positive, then as tau goes to infinity, so remember, when tau goes to infinity is the same thing as t goes to 0 from below. So if this factor is positive, then as tau goes to infinity, formally it starts to dominate. And then you really shouldn't have this picture. So if you're having blow-up that lives at this scaling, blow-up that lives at this scaling is only admissible if this exponent is negative. So if you have that s is greater than alpha, you should have no blow-up. And s less than alpha, the blow-up, OK, it's no blow-up at this scale. And if s is less than alpha, then you should have blow-up, which looks just like the Euler blow-up. Or sorry, not Euler, Burgers, which looks like the Burgers blow-up. So what you can actually do, and this is what Pasqualotto and O did, they just take the Burgers blow-ups and they just try to put them perturbatively into this equation. And they have a self-similar structure, which you can look at. And this term here looks perturbative. I mean, when you go to very long times, it's not there. So this equals 0. So you already have the kind of obvious scheme for how those blowups should also appear in the viscous setting. All right, so when S is less than 1, you can always find one of those self-similar blowups, which is, so when that countable family that I was writing, it's like alpha is 2/3, 4/5, 6/7, etc. So when S is less than 1, you can always find an alpha which is less than 1. And even though that blowup might be very highly unstable, it's still perturbable to the viscous Burger setting. OK. I'll just say a couple more things. So the Euler equations, they also have a 2-parameter family, I mean, like Burgers, of scaling symmetries, because you can rescale length and time independently. And so you might have the idea, which people have, which is that if you have self-similar blow-up for Euler, then you can try to see what happens to it at the Navier-Stokes level. You just plug it into Navier-Stokes, and you see whether the viscosity term should matter or not. So, and if you find self-similar, if you're so lucky to find self-similar blow-up for Euler, where the scaling is such that this factor would look perturbative, then in principle, you might be able to solve the Millennium problem. OK, but there are many steps in there. This idea, if any of you have looked at Tao's paper on dyadic models, he's using this at a kind of dyadic level. His viscosity is perturbative. And also, if you've looked at the work on implosions for 3D barotropic compressible Euler, they're also using this idea to perturb the implosions for 3D barotropic compressible Navier-Stokes. So that's probably enough for today. So thanks.
So are there any questions?
That was very nice, Dallas.
Thanks.
So you were talking about the linearization.
Yeah.
In particular, you're saying that there's only for alpha equals 2/3. Do you actually have stability in the linear problem as well?
That's correct. Yeah. Although actually, you gave me a chance to talk about something I didn't get to talk about. So actually, so even in the alpha equals 2/3 case, you're going to have it. If you linearize, it's going to look unstable. So in other words, I write alpha equals 2/3. I write down the linearized operator. So then you linearize in self-similar variables. Self-similar variables. So you get, and then you're studying this eigenvalue problem. And even for alpha equals 2/3, you're going to have eigenvalues in the right half plane. And maybe you know this, but it's for everyone else. It's those eigenvalues come from time and space translation. So nearby these self-similar solutions, I mean, if I make some translation, then I've moved where the singularity happens, and because the solutions are singular, that actually looks like a really big change. And so, in particular, some people have written. There's some papers that talk about if any Euler blow-up should be unstable, but it doesn't actually account for this. So there are eigenvalues in the right half plane, but they're due to symmetries, and so they can be modulated away. Then yeah, if alpha is 4/5, then they're just 2 more eigenvalues. Every time you go up, you get 2 more. But it's yeah.
And can you still mod out the stabilities when you have viscosity?
When you have viscosity, you can still mod out. You can mod out the symmetries, and you can. I mean, you can land yourself. You can land yourself on the stable manifold, and that's what O and Pascual-Loto are doing. Yeah. Yeah.
Are these all the possible props orders?
So there are also ones where alpha is not integer, and so if you, and also there's some other ones, but the place, I'll just say the place to look. So the oh, look at this. The place to look is Collot, Gould, Masmoudi, Burgers with transverse viscosity. Because I didn't write any theorems, I didn't really prove anything here, but they actually do rigorous proofs of classifying. Okay, if it's analytic, it has to be one of the integer ones. If it's Holder, it has to be something else. So they find some additional ones, which are discretely self-similar. But I only learned that last night while preparing. So.
And about this, when you, or perhaps let's say a first question is, can you give a vague idea of how Pascual-Loto who do the construction? What are the,
well,
how do you see the main points of that paper?
Yeah, but it's like the one that we do.
Okay.
Except that, you know.
Well, viscosity has reverse sign, no?
Yeah, but I mean, in our case, backward in time, viscosity is going to 0. Their case, forward in time, viscosity is going to 0. So it's a lot like what we did.
Okay.
Yeah.
And then
yeah.
I didn't get fully this part about instabilities that come from symmetries.
Yeah.
Because,
yeah. Mm-hmm.
I mean, perhaps it's also important where you look the eigenvalue problem, I guess, no? Because these ones will be singular eigenfunctions or not?
They'll be smooth eigenfunctions. It's just that when you make this ansatz, you should really write. When you make this ansatz for Burgers, you should really write capital T minus little t, 1 over alpha minus 1, u, x minus x naught, capital T minus t to the 1 over alpha. And if you differentiate in capital T, so you look at d capital T u, or d x naught u, then those should formally solve the linearized problem. So if I call this u bar, then these should formally solve the linearized problem. dt u bar plus dx dt u bar u bar equals 0. And if you turn that into similarity variables, then you find eigenfunctions. And they have positive real part. So so you need to write the similarity variables for this linearized equation. And then you'll find, for the time translation and the space translation, you'll get eigenfunction with positive real part.
Okay.
Yeah. I'll put it in. I'll put it in
forward similar? Is there something similar?
Forward self-similar?
Yeah, if you look.
That I for the forward self-similar problem, I don't think so, because you really have you have data there which is kind of constraining you.
Mm-hmm. Okay.
Yeah. So. But yeah.
Thanks.
But I'll have to think about that.
So, any more questions, remarks? If not, I have one. So, are there is a spatial configuration of parameters, exponents in such a way that there is an invariant norm by scaling or not?
So if you for the Burgers case, if you pick a norm which you want to have invariant, then that will let's see. If you pick a norm you want to have invariant, that will narrow your list of parameters. Yeah, it'll reduce. Yeah, if you pick a norm, that's like one. Yeah, so if I pick C 1/3 for C dot 1/3, for example, then okay, that'll narrow my 2-parameter subgroup to a 1-parameter subgroup, and if I pick C dot 1/5, then that'll similarly narrow it. Is that helpful, or is that did that somewhat answer your question?
No. Just wondering if there is a spatial, some kind of spatial configuration in which you can identify an invariance by scaling in some spatial norm, maybe fractional, I don't know. But because when you have this kind of invariance, usually is some limiting case, no?
Yeah, right, yeah,
that
right.
would be interesting to figure. I'm not an expert of this kind of problems, so.
Well, you're thinking of a time-independent problem?
Yes, I'm thinking
okay.
in time-independent
I see,
problem.
yeah.
So we resume this morning session. It's a great pleasure to introduce Professor Crippa from University of Basel, and he's giving a talk about anomalous dissipation in fluid dynamics. Please.
Great, so thanks a lot. So I'm very, I hope you can hear me, so if not, just let me know. So I'm very grateful for the invitation. I'm happy to be here, and so this is based, so my talk will be based on 2 joint works with a few people in Luigi's family, so you have to like this talk because it's, it's also due to you. And this is about anomalous dissipation in fluid dynamics. So we have already seen so this partial differential equation, so I will just briefly review also in order to set the notation. So the incompressible Euler equation takes this form. So V is the velocity and P is the pressure. So we are considering the incompressible case. So divergence of V equal to 0. And this equation expresses the conservation of the momentum for an homogeneous incompressible inviscid fluid. And we consider this equation either on the full space, so no boundary conditions, or on the torus, okay, so periodic boundary conditions. So this equation comes with a formal energy estimate, so for the kinetic energy. So if we scalar multiply our equation with V, we get this estimate here. And then using the divergence-free condition on the velocity, this formal estimates leads to the conservation of the kinetic energy. So if we define the energy to be 1/2 the integral of V squared, then the kinetic energy at time t, at least formally, equals the initial kinetic energy. So if we consider instead the case in which we have some viscosity, so we get the Navier-Stokes equations. So you see the differences here are that we have nu times a Laplacian on the right-hand side. Nu is the viscosity. So we are now modeling a viscous fluid. Okay, so physically, so if you have two layers of fluid sliding one on top of the other, you have interactions between them. Yeah? You have a kind of friction between them. And consequently, the energy for the kinetic energy gets modified by this minus nu times gradient square term, and also the balance of the kinetic energy. So you have this dissipation of the kinetic energy at a rate which depends both on the viscosity, nu, and on the gradient of the velocity, so on the regularity of the velocity field in a sense. So in the inviscid case, energy is conserved, formally at least, so provided we can do these formal computations, while in the viscous case, the energy is dissipated at a rate which depends on the viscosity and on the regularity of the solution due to the appearance of the gradient. All this is formal, so I did a lot of computations. We didn't check whether we have enough regularity to perform that, and this will be key to the following. So the right context for solutions of Navier-Stokes is that of Leray-Hopf solutions. So you, Dallas, were mentioning that. So one can indeed construct a solution to the Navier-Stokes equations. This has been done by Leray and Hopf, which satisfy the energy balance, but in the form of an inequality, not in general as an equality. This is formal, as I was mentioning, and indeed in 49, Onsager already predicted the possibility of having dissipation without the assistance of viscosity. So with this sentence, that the turbulent dissipation could take place just as readily without the final assistance of viscosity, because the velocity field does not remain differentiable. Okay, so you have a sort of a balance between the term nu, which is small, and gradient of the velocity squared. So the velocity becomes irregular. So they might, in principle, strike a balance and remain bounded away from zero, in principle. This is the scenario that he predicted. And around the same time, Kolmogorov, in his K41 theory of turbulence, he stated this in an even stronger sense, if you want, via the zeroth law for turbulence. So predicting that the dissipation, so nu times the integral of the gradient of the velocity squared, should be uniformly bounded away from zero, uniformly in viscosity, where these brackets denote something which in the Kolmogorov theory is quite unspecified. So might be some averaging in space, time, depending on whether you're modeling something ergodic, or if you believe into a statistical theory of turbulence, this could be even an ensemble average, okay? So with respect to the probability measure on the space of solutions. There is a difference, I will not comment a lot on that, between 3D and 2D. 2D is more special, you have more conservation laws, so you have inverse cascade, but I will not enter into that. That's mostly a disclaimer. The process, so the kind of the process you should keep in mind, should have in mind is the following. So you have a nonlinearity in your equation. So this nonlinearity produces a cascade of information to high frequencies, so small spatial scales. And there, the viscosity has a stronger effect. So you have a sort of enhancement of the viscosity. And this is the place where you can expect to have a balance. So even if you have small viscosity, but you have creation of very high frequencies, then you have a stronger effect of the viscosity of the Laplacian, and then this becomes uniform in viscosity. So this is the sort of process you should have in mind. So this theory is, experimentally and numerically validated to a very large extent. There are corrections, though. There are intermittency corrections. Again, that's another thing. I'm not really an expert, and I will not enter into that. But there are a lot of reasons to believe that, a bulk of this theory is correct. But there is basically not a large mathematical verification of it. And things are starting now in a certain sense. So let's try to understand what is so for the Euler Navier-Stokes equation, what is the critical regularity which we believe should be important. So you already had 1/3 earlier, so 1/3 will appear now. So if you formally manipulate the nonlinear term in the energy estimate, so V dot grad V scalar multiplied with V itself, you can just start swapping things around. So you have one gradient, here you have 1/3 gradient to the power 3. I have 3 V's, V to the 3. Okay, that's a formal computation, a formal rewriting, and this was, it's one way of saying the scaling in the Onsager conjecture by now Onsager's theorem. So if you consider C alpha solutions of Euler, so alpha means when you consider increments, so they scale like the increment in the independent variable to the alpha. So the prediction by Onsager was that energy should be conserved if alpha is at least 1/3, this magic number. And this is sort of easy in the sense that you can regularize the equation and study commutators. Okay? And this has been done by many authors and usually goes under the name of Constantin ATT commutators theorem. So he also predicted that below 1/3 regularity, energy can be dissipated by the implicit equation. And this indeed has been shown after 15 years of work by convex integration initiated by dell'Ellis and Székely-Hidi, by Izet and Bookmaster, dell'Ellis, Székely-Hidi, and Vicol in slightly different setups, with convex integration also providing examples of non-uniqueness for these equations on top of the dissipativity. One issue there, and I think here reference is Yunju probably. So energy can grow as a result of this these convex integration schemes. So you can, or said in a better way, so you can prescribe a profile of the energy. So you can, with the same technique, basically construct dissipative solutions or solutions which have other behaviors for the energy. So even growth of the energy, or maybe local increase of the energy in some area. Okay? This is in connection to the next points. So the Kolmogorov theory of turbulence asserts that this type of dissipation, so the existence of dissipative solution, should not just hold for the limit equation, for the implicit problem, not just for Euler, but should hold uniformly in the vanishing viscosity limit. So the solutions that you should think as physical should not just be kind of, isolated singular Euler solutions, should be solutions that you can achieve as vanishing viscosity limit. Okay? And this being vanishing viscosity limit brings with itself the fact that the energy should decrease globally and locally. Okay? So in this sense, it's difficult to push convex integration schemes to become uniform in the vanishing viscosity limit. Okay? This has been done to a certain extent by Bookmaster and Vicol, but for weak non-Lereo solutions. Okay, so for solutions of Navier-Stokes which do not satisfy the energy inequality. Okay? That was an important step, but still sort of incomplete. And another very difficult part, I was mentioning that before, so there is no mathematical understanding of this statistical theory of turbulence, or it's very limited in a sense. So this universality, so these are the solutions that one typically sees in real fluids. Okay, so this is very, very open. It's open, that my pointer collapsed. Okay. So, and then a question which maybe it's more a mathematical question than a physical question, I don't know. So all these constructions, they also come with extreme non-uniqueness, so you construct infinitely many solutions. Of course, you might wonder whether, fine, so there are multiple weak solutions, but maybe only one is selected by some selection mechanism, by vanishing viscosity, by some regularization of the equation in some way. So for instance, for scalar conservation laws, so for Burgers, this is the case. You have multiple weak solutions, you have one entropy, or one vanishing viscosity solution. Okay, that's a question we can ask about these equations from fluid dynamics, but still kind of very open though. Okay, so since the nonlinear case is very ambitious, so we looked at a kind of easier case in which we could still produce some nice and significant, in our opinion, results. So that of scalar turbulence. So the physical model you should think of is you have a scalar, so the temperature, which is passively advected by a turbulent flow. Okay, so velocity is given. Theta is the temperature. Okay, and the temperature just rearranges itself according to the fluid. It's a passive scalar, meaning there is no feedback. Okay, so the velocity is given. We are assuming that there is no that the distribution of the temperature does not affect the velocity of the fluid. Okay, so there is a background velocity which is just given. Can be passively advected or passively advected and diffused with some diffusivity. Okay, kappa, and here I get the advection diffusion equation, which is now a linear equation in theta, and u is the given velocity. And then we can start doing the same things that we have seen earlier for the nonlinear case. So we have a formal L2 estimate for the solution, which reads in this way. And you have here some dissipation, which is again depending on kappa, so on the dissipativity, and on the gradient of the solution. Here we use a divergence-free condition to get this formal estimate. And we can redo this formal rewriting of the nonlinear term. Okay, so in the energy estimate, so the nonlinear term was u dot grad theta, scalar multiplied with eta. So now we pick a parameter alpha between 0 and 1, and then you can share derivatives. So you can give to u alpha derivatives, and to each theta 1 minus alpha over 2 derivatives. Okay, you have this formal rewriting, and we can believe that this formal rewriting gives to you the criticality threshold. Okay, this goes under the name of Jaglom's relation. So if u is in C alpha and theta in C beta, then the important quantity is this alpha plus 2 beta, okay, because it's 2 thetas here. So if it's greater than 1, we are in the subcritical case. We have too much regularity. The critical threshold is equal to 1, and the supercritical case, in which we should see interesting things, is alpha plus 2 beta less than 1. Okay, so this is not like our discovery. So this goes back to these two physicists or applied mathematicians, Obukov and Korsin, in 49-51 on the two sides of the Iron Curtain. So at the time there was not much communication. So they predicted, stated, or empirically conjectured that in the subcritical regime, so a lot of regularity, one should have uniqueness. So here uniqueness, which you don't have for the Euler equation, or you don't expect even, or you cannot prove in the Euler equation easily, even if in the case regularity above 1/3, because of the linearity, okay, and conservation of the L2 norm. While in the supercritical regime, they were predicting non-uniqueness, dissipation of the L2 norm for the inviscid equation, and even more, uniform in viscosity dissipation of the L2 norm, which amounts to what we call anomalous dissipation. So for a family of solutions of the advection effusion equation, equibounded in the C beta space, okay, so alpha is the regularity of the velocity, beta of the solution, you have that the dissipation of the energy along at least a subsequence is uniformly bounded away from 0. The subcritical case is sort of easy, so you can again redo a proof via Constantine ADD commutators, so that's not very complicated. The supercritical case, while it becomes also a matter of which question you're really asking. Okay? So are we interested in producing one velocity field and one initial datum, for which the family of viscous solutions exhibit anomalous dissipation? Or one velocity field and then universality in the solution, or at least in a large class of solutions, or one can be even more ambitious and try to develop here a statistical theory. Okay, so what we did is the following. So in the and this is the first paper with Maria and Massimo Sorella, so a student of Maria in Lausanne. So in the supercritical regime, so alpha plus 2 beta less than 1, we produced an example of anomalous dissipation for one velocity field and one initial datum. Okay? So we constructed a velocity and an initial datum, which is tuned in a sense to the velocity, such that, which is the same for all kappas, so for all diffusivities, such that the family of the viscous solutions, of the solution of the advection diffusion equation, produce anomalous dissipation. So that's our main result. So this came together with something which gives an answer in the linear case to the selection question. You remember, so in Burgers, there are multiple weak solutions, but only one is a vanishing viscosity limit. We disproved this for the linear transport equation outside of the good regularity classes of the Di-Pernal-Lyons theory, for instance. So lack of selection by vanishing diffusivity. So you can have multiple solutions of the transport equation, and several of these solutions can be obtained by taking a vanishing viscosity limit. So you will have multiple subsequences such that the limit point along the subsequences are this multiple solution. And the same under convolution of the velocity field. Okay, if you regularize not by adding viscosity, but by regularizing by convolution the velocity, the same will happen. So we take a Lagrangian approach, which means the following. So, well, I will not go into the full proofs of this theorem, but I will give you a glimpse at some of the tools and some of the ideas that we use. Okay, the paper is not super long, but there are quite few technicalities, parameters, or things which are a bit complicated to explain in a talk. But I will give to you the tools at least. So Lagrangian approach means the following. So for the transport equation, okay, U is given, theta is the solution. You have a flow, a deterministic flow. Okay, solves this equation here, dODE. And then the solution is just the push forward of the initial datum along the flow. Okay, so you go backward in time along the flow. You see which value the initial datum had at the corresponding point where the backward characteristic hits t equal to 0. Okay, that value is the one transported. Well, if you have now some diffusivity, so if you have the kappa, you have now the stochastic Lagrangian approach. In that, you can consider a stochastic flow, which is just this thing here. In this case, it's sort of simple, meaning basically you can reason, quenched, that is, so trajectory by trajectory. So the easy way, if you're not really working in probability, to see all this is you have a parametrized family of trajectories, which is this Brownian motion. And then for every value of the probabilistic parameter, you solve an ODE with a forcing, with a trajectory here that you're adding. And then you have Feynman-Katz representation formula, which tells, okay, so for every value of the stochastic parameter, do your push forward, and then take the expectation. Okay, that's the layman version of this formula, which is basically what we use. We don't use very fine properties apart at a couple of places. Again, so W is a Brownian motion. Informally, you should think of it as a probabilistically parameterized family of trajectories with two properties. So you have a law for the increments, so they're Gaussian. And the other property which we use at some point is they are isotropically distributed. Okay, so the Brownian motion is not telling to you go more in the direction of the door rather than in the direction of the back of the room. Okay, so it's isotropic in space. Okay, so the basic idea in the construction is we go back to a famous construction from the theory of mixing, which is the so-called Depot-Bressan checkerboard or chessboard example. So we do some modifications, though, because of some reasons I will tell you in a little bit. So we don't do convex integration, so that's maybe something new, but since Maria did a lot of convex integration, we have Q. So it's TQ and AQ, so the index is Q, and we didn't have any fights about that. So we pick a sequence of times, TQ going to 0, and the sequence of space scales, AQ going to 0. Such that the following happens. So things happen at the beginning. So there is a first stage for time between 0 and 1. So you have these special times, 1 minus TQ. So this converges monotonically to 1. At time 1 minus TQ, your solution to the inviscid problem, so the theta, is going to take value plus or minus 1 on a chessboard of side AQ. So at each step you do a refinement, you do things in between, and you do a refinement from scale AQ minus 1, which is much larger than the scale AQ at the next iteration. Okay? Things happen in between via shear flows. Okay? So at appropriate space scales. Okay? So you realize this step by moving stuff on the torus using shear flows, and also these shear flows are picked at suitable scales. So you do something here, and then you kind of break horizontally your squares, and then you do another vertical move, and then you can do this rearrangement. You can do this rearrangement here. It's important that also the shear flows have a suitable scale. So you should think, to get a picture in your mind about a dyadic sequence. In that, at every step you refine by a factor 1 alpha the scale of the chessboard, and you do that in dyadic times. But that's not what we do. So we need AQ, which grows super exponential, out of two reasons. So one reason is at some point we will need to separate scales. So we will have to do something between AQ and AQ plus 1. And second, also in order to optimize the regularity of the construction. So this choice of AQ will be important to that effect as well. So basically what happens is that you run this procedure at the singular time t equal to 1. You have realized what you may call perfect mixing. Okay? Your solutions converge to the weak limit, okay? To something which is 0. Afterwards, you can decide, okay, I change my mind, I reconstruct large scales. Okay? You play the same game, but now backward in time. You reconstruct the chessboard at a time t equal to 2. You have again your initial datum, okay, things at scale 1. So this is like the basic mechanism for the inviscid equation for the pure transport. Okay. So let me start because it's easier to visualize, to tell you how the non-selection theorem, so the third one, so the lack of selection under convolution of the velocity field, how that works and what is the exact question we want to answer. Okay, I do that out of two reasons. So one, because it's easier to visualize and less technology. Second, because it was also the first theorem that we proved, and then we flipped them in the presentation of the paper. Okay, so the question is the following. So you might still keep the transport equation, so without any regularization by diffusion, so no diffusion, but you might consider the following question. So instead of U, I regularize U in some way, by convolution would be a canonical way. And then this regularization by convolution gives me a solution, theta epsilon, which is not the convolution of the previous solution, okay? It's the solution with the convolved velocity field, okay? You might wonder whether, fine, although the limit equation might have multiple solutions, whether theta epsilon converges to a unique limit point, which would be the cutest solution of the limit equation. Okay? The answer is no, because we are disproving that. And the idea is, one way to get an understanding of what we do in order to disprove this theorem is the following. So, what is convolution doing? Convolution is taking averages over radius epsilon, right? So filters everything which has a scale below epsilon, because things have zero average on some scale depending on the step at which you are. Once you have a convolution at the scale epsilon, everything which has a finer scale is gone, okay? Maybe with some errors, but it's basically gone. So convolution filters shear flows with scale below epsilon, okay? That's the first element. Which implies, so you run your mechanism, so you almost get to the singular time t equal to 1 in your mixing, but at some point there is a precise time at which the convolution starts filtering before the effect is kind of negligible. Again, you have a lot of errors that you have to estimate, but think before that's negligible. So, but then what happens is that theta epsilon does not get fully mixed at time t equal to 1. Okay? Because at some point the velocity becomes 0 because I'm filtering it out. Which means theta epsilon stays at some fixed scale of the order of epsilon, the scale of the solution, okay? Goes through the singularity unchanged because there is no more singularity, and then large scales are reconstructed, okay? Then I'm basically doing nothing until now, right? I'm just saying, well, I forget what happens around the singularity, but okay. Then afterwards, I redo what I was supposed to do. But then and here is the tilt. So for t greater than 1, so when you have the reconstruction of the large scales, you don't just do that. You also do another trickery, which is at every step, you also do a swap, okay? So you introduce a swap move, which does the following. So it basically swaps the black and the white tiles, okay? So you're reconstructing the chessboard, and then when you pass from scale AQ to AQ minus 1, you do that, and then you swap the tiles. Then when you pass from AQ minus 1 to AQ minus 2, you do that, and you also swap the tiles, okay? Every time you do the swapping. Which implies the following. So this you only do after a singularity, okay? Not before the singularity. For the singularity, you refine. After the singularity, you make something less fine. So you coarsen, swap at every step. This implies the following. So depending on the parity of epsilon, in a sense, depending on how many swappings you have left after you have done this filtering, the following happens. So you are reconstructing for time t at the end of the process, for time t equal to 2, you have reconstructed either an even or an odd chessboard, depending on whether the sequence of epsilon was kind of odd or even in a certain sense, okay? Depending on how many swaps you are living. Okay? This is the idea of the counterexample to this selection. So let me mention that, okay, this is a counterexample to the selection under convolution. There were previous examples which disproved the possibility of selecting a unique solution under some regularization of the velocity, not done by convolution, meaning the following. So both these two examples, by myself with Stefano Spirito and Gennaro Ciampa, and by Camillo Dell'Elsin and Vikram Giri, they were answering in the negative the question whether is it possible to find some whether for any regularization of the velocity, the regularized solutions would converge to a unique limit. Put in another way, both these papers were constructing a velocity field and some regularization of it in such a way that these solutions with that regularizations would converge to multiple limit points. These regularizations of the velocity were not done in such a canonical way like a convolution. Okay. Here we do that under a convolution with a general kernel. That's the improvement. So, okay, so we already understood a little. So we have this idea of filtering for the convolution. Let's make now a parallel, So what are the phenomena which happens if you replace filtering the velocity field by I have diffusivity, I have my kappa Laplacian on the right hand side, okay? So what is the picture we should have in mind? So what happens is the following. So the differences are the convolution acts on the velocity while the diffusivity of Brownian motion acts on the trajectories. You are adding the Brownian motion in the SD. So the scale here is of the order of epsilon, while here the scale, okay, so scale meaning at which distance, so at which spatial distance things act. So here, well, the scale at which the action takes place depends on the diffusivity, but also on the time you let things act. Okay, so if I have some diffusivity acting for a time tau, then I have an influence which depends on the product, tau times kappa, okay, or on the square root of it, depending on. But okay, depends on the product of these two quantities. In particular, and this is important for later, so if for some reason I decide that on some time interval I put no velocity, u equal to 0, so the convolution does nothing, while still you have some damping due to diffusivity because we have a convolution with a Gaussian for the solution. Okay, you still damp the solution. You have a heat equation on that interval. Great. Then okay, so the last thing is, well, it's not literally true, but for our effects, in a certain sense, so the convolution has infinite propagation speed, meaning the following. So I see I kind of do epsilon averages in no time, okay? while, so due to this Gaussian distribution, with 99.9% of probability, the effect of the convolution with the Gaussian kernel is bounded. So in a sort of, wrong sense, a very informal sense, so I'm saying that we have finite propagation speed with high probability for the diffusion equation. Okay, it's a strange statement, but okay, if you look at what we do, we make with high probability this type of statement effective. Okay, sounds a little strange to put it this way, but fine. Okay, so we go back to our example. So you have this chessboard at time t equal to 0. You find and refine. You refine the scales. Singularity at time t equal to 1. And then, okay, let's play a little bit with scales and frequencies. Okay, for time between 0 and 1, you have your advection. So the advection refines the chessboard at each scale. Okay, what we do is that inside its stage, as before we did after time t equal to 1, we added this swap move. What we do now, we add a pure diffusion stage at each step, in the following. So we reserve some small time intervals between these transitions from one scale to the other, in which we set the velocity to be equal to 0, and we only let diffusion act. Okay, we have a pure heat equation in those intervals. And then, okay, then we're lucky, so we're smart, I don't know, so we decided for this separation of scales. So AQ is super exponential. This implies the following. So this implies that corresponding to the diffusivity kappa, there is a critical time which, when kappa goes to 0, the critical time goes to 1, such that the following happens. Before the critical time, diffusion is just a perturbation. Okay? Basically, the solutions behave like solutions to the linear transport equation. Again, errors to be quantified. Basically, it's like that. And then, around that critical time, you have a purely heat equation stage. Okay? You have put no velocity inside there. Then there is a tiny interval of time in which you have the heat equation. This will dissipate your solution because it's the heat equation. You can write down your formula. Okay, okay, diffusion is dominant, is the dominant effect. But of course you should, object, but okay, so this stage, since you are, packing everything to time t equal to 1, these intervals of time, they are becoming very, very tiny. And your damping with the convolution with the Gaussian, well, has less effect since these things happen for a very small time. But there is something saving us and striking the balance is what you can call enhanced diffusion. Okay? Remember that you prepared your solution to be high frequency, and the small diffusivity didn't damage that too much before the critical time because this was a perturbation. So enhanced diffusion, well, it's a field by itself, but the baby example, just one line, what this is the following. So these two functions here, okay, are both solutions to the heat equation, to the same heat equation. Okay. Here you have frequency 1 and you have decay e to the minus t. Here you have frequency 10 and you have a much faster decay. Okay. You can see that by writing that in Fourier, right? So if you have very high frequency, then things are damped faster. Okay. And then this is what gives the balance. So the small time in which you have the pure heat equation is balanced by the fact that you have very high frequency of the solution, that you prepared exactly for that reason. So in that tiny interval of time, you kill a given, so a fixed amount of the L2 norm of the solution by the heat equation. So that's the principle, okay? So we get dissipation of a fixed amount of this solution. Again, that's the principle in that I swept under the rug like 2 tons of things. There are a lot of technicalities in all this. I mean, it's not a super long paper, but still you have to work to achieve what I stated. So I didn't say anything about the lack of selection under vanishing viscosity. So basically, I convinced you of 2 results. So the lack of selection under convolution and the anomalous dissipation. So in order to show the lack of selection under vanishing viscosity, you have to find another sequence, subsequence of diffusivity is going to 0, such that something different happens. And that's again some work, and this relies on some suitable cancellations due to the isotropy of the Brownian motion. Okay? So the principle is that under vanishing viscosity, you can converge along one subsequence to a dissipative solution, along another subsequence due to different mechanisms to a conservative solution, or at least to a solution which dissipates less than the previous one. I think we do that for a conservative solution, for a fully conservative. Another thing which I was hiding is, while I was telling you, so alpha plus 2 beta less than 1, now we reason with checkerboards. They have discontinuities. Okay, you have to regularize that, and you have to pick a lot of parameters along your construction in such a way that you can get that regularity with also suitable integrabilities in time, which is another issue. The regularity of the solution is something that we also do separately, and that relies on some regularity for the stochastic flow. Okay, so for the stochastic flow, we show that has Holder regularity in space. Okay, there is an issue. So with our construction, so what happens is that in a certain sense, and you might argue whether it's physical or not. It's difficult to give an answer. So the loss of the L2 norm happens only at the final time, meaning the following. So for every epsilon positive, if you look at the dissipation, so nu integral between 0 and 1 minus epsilon, for epsilon fixed, that goes to 0. Okay? So in a certain sense, so the energy, the smaller the kappa, the more the dissipation of the energy concentrates at time t equal to 1. Then the question, for which I don't have a true answer, is, well, is that really physical? Well, on the one hand, so typically turbulence is isotropic, so you don't have a preferred time, a preferred space. Okay. In fact, so two students of Maria, so Massimo Sorella and Carl Johansson, they engineered our example in a sense, producing dissipation which is now continuous in time, but it becomes concentrated in space. So they sort of bargain, to the best of my understanding, the two concentrations. On the other hand, there are also, corrections to turbulence theory which allow for intermittencies. So things happens, are also observed to happens, at spots, Dissipation can be concentrated on lower dimensional sets, and that's an area of active study from both the experimental, numerical, and mathematical point of view. So these are two papers to which I can point, by Luigi De Rosa and Phil Isett, and by Luigi De Rosa, Theo Drivas, and Marco Inversi. So after the completion of, before and after the completion of our work, there are two other papers which are related. So there is a paper preceding our by Drivas, Elghindi, Ayer, and Jijeong, in which they also construct examples of anomalous dissipation without regularity for the solution. Okay, so they sort of maximize the regularity of the velocity. Velocity is C alpha for every alpha less than 1. They also have a point in time singularity, no regularity for the solution. The second thing which marks a difference between our and their paper is that they argue by a different technique, so by some kind of criteria for anomalous dissipation. And the very type of proof that they use via this criteria does not allow them to produce vanishing diffusivity sequences, subsequences, along which you do not have dissipation. So in a sense, their technique of proof does not allow for a non-selection result, but only for the anomalous dissipation result. So these are two differences. More recently, so Scott Armstrong and Vlad Vikol came up with a new technique of proof of anomalous dissipation by fractal homogenization. And what they do in what is on the archive now, so they announce also further results, which are due to appear. So they can prove anomalous dissipation, continuous in time, so without this everything happens at the final time, by velocity fields which are C1/3, so at the critical regularity, but without showing regularity for the solution. So they announced that to be deferred to a further, so to a future paper. And so the proof is completely different. So they rely on homogenization techniques, and in a certain sense they have something. So our velocity field. So we have this sort of cascade of frequencies when time goes to equal to 1. Okay, and we have active scales, small scales smaller scales when time goes to 1. So in their construction, you have more scales. So you have all scales at all times, in a sense, and that's responsible for this continuous in time diffusion. Okay, that's a much more technical paper. It's some 120 pages paper compared to our 30 or so pages. And if I have a bit more time, which I assume I have, which is great, thanks. I will just say a couple of words about an application to the Navier-Stokes equations. So for that, we joined forces with Elia Brouet and Camillo Dell'Ellis, where the previous result about anomalous dissipation for Navier-Stokes. And joining forces, in a sense, we could optimize the regularity and get also a non-selection in the result. So basically, we consider what it's usually called a 2.5 dimensional system. This means the following. So you are in 3D physically, but you have in the background a 2D equation. So you have a 2D velocity, which satisfies a 2D Euler or Navier-Stokes equation. Then you have a third component, which is the D third component, which is passively transported by the background 2D velocity. Okay? So you are in 3D. You have three components, V1, V2, and theta, which is transported, but you have a sort of symmetry or a major constraint, so you have a lot of 2D geometry in that. Okay? So the velocity V of the full system has this form, U theta. U solves a 2D equation not involving theta, so U is determined by itself, and theta is advected and diffused by U. Okay? This is what it means, 2.5 dimensional. Okay, so loosely speaking, in order to produce this example, we do the following. We take U and theta from the previous paper, okay? And then we say, okay, we would be super happy, enthusiastic, if you would solve the Navier-Stokes equations. Why should it? Okay, so it's a velocity something. Okay, so it always solves a Navier-Stokes equation if you say, okay, I put a forcing, and the forcing is the amount, is the error. So my solution does not solve the Navier-Stokes equation, and I call F nu the defect. Okay, so F nu is this amount here, so the du minus nu Laplacian. So we are using shear flows, so you do not have this nonlinear term. Okay, you also are pressure free. In fact, if you look again at the fact that you have an explicit solution U. Okay, shear flows. Okay, so then U almost solves a Navier-Stokes equation, with the viscosity-dependent forcing on the right-hand side. Okay, so also you Dallas, you're going to speak about forced Navier-Stokes equation. Here the forcing comes for kind of not exactly the same reason, but again is sort of in the same spirit. Nice. Okay, so what we do is putting everything together. We show anomalous dissipation and lack of selection for the 2.5 dimensional. So by completing this U to V, which is now viscosity dependent, by putting in the third component the theta nu. Okay, so the solution to the advection diffusion for nu, which is now you optimize all the regularities. So alpha plus 2 beta less than 1. You give the same amount of regularity to the solution and to the velocity field, 1/3 to all of them, you get back to the on-cycle critical regularity. Okay? Until now, sounds sort of slightly tautological because we have here this forcing, But okay, let me make some remarks on that, and then I will close. So first, we can arrange F nu and the forcing to be smooth, and the solution to be the unique smooth solution of the approximating Navier-Stokes equations. Okay, we can do that by truncating away from the singularity, basically, and controlling several things. Okay, so the objection one might have is, well, fine, any function solves any equation if you put a forcing, which corresponds to the amount by which the solution does not solve, the function does not solve the equation. But our theorem is not empty, because, well, the point is we recover some physical meaning because we have some bounds on the forcing, okay, in suitable spaces. So these are regularity spaces, basically, so for the regularity spaces. For spaces under which there is no linear anomalous dissipation. Okay? So if you have very poor regularity on your forcing, you can have anomalous dissipation just by adding a forcing to the linear heat equation. This is not what you want to model. So you want that anomalous dissipation comes from the fact that you have a nonlinearity. Nonlinearity pushes to high frequencies, and there the dissipativity or the viscosity are more efficient. Okay. So, and this is what I'm summarizing here. So if we only had bounds in, say, L infinity of space, the heat equation alone could display anomalous dissipation. Right? But we can get better bounds, so C sigma bounds for some positive sigma on the sequence of the forcing, and these bounds are sufficient to prevent linear anomalous dissipation. Okay? So in a sense, we still recover the result in which the anomalous dissipation comes from this cascade to high scales, and then bang, enhanced dissipation. Okay, so anomalous dissipation again is due to the cascade, which is due to the nonlinearity. Also, together with this, we also get a result of lack of selection under vanishing viscosity. So in this particular setup, you cannot hope for recovering uniqueness of a privileged solution of Euler by vanishing viscosity. So this is also disproved. Of course, what's left open is the possibility of doing the same, and this seems to be kind of far from our techniques, for the unforced equation, or at least forced but with a forcing which does not depend on the viscosity. Okay, so these are interesting questions in our opinion. And also this is 2.5 dimensional. So what for me is also very interesting is the question whether in 2D anything better or worse, depending on your optimistic or pessimistic point of view on turbulence happens. So in 2D you have this very special structure. You have vorticity that's transported, and then if you do experiments or you run simulations or you run numerics, you see that something different happens. So you don't just have very fine scales, so you don't have just high frequencies, but you also see, that really is seen in numerics and experiments, you also have formation of large blobs. Okay? So you have this inverse cascade, so you have formation of larger structures, and this is due to the additional conservations that you have in 2D. Okay? That's something special, and to me, a very natural question is, can you do anything better in 2D under vorticity bounds? In fact, if you look, you take one step back and you see what can be done under, so with convex integration techniques. So these techniques do not really work for the 2D Euler equation with integrable vorticities. Okay, there are some results due to Maria and Elia in which they almost do L1, so they do L1 weak or other Lorentz spaces. But for me, it's very interesting to ask this question, whether in 2D under vorticity bounds, whether better things in terms of selection can be said. Is it true that vanishing viscosity there selects a unique solution, and that's totally open to the best of my knowledge? Thanks a lot. So that'd be all.
Many thanks. Many thanks, Gianluca, for the nice talk. Are there questions? Remarks? We have one over there.
So presumably you have to pick these super exponential scale separation so that you can approximate linear evolution or the inviscid evolution by the viscous, or show that they're not too far apart.
Yeah.
But if you look at Abakov course and spectrum produced by nature, right? You have broadband sort of spectrum in both the velocity field and the scalar. Do you think there's any sort of way, any hope that you can construct solutions that have that aren't just separated in little peaks in the spectrum? I know that's probably a very hard question.
That's a very good question. Yeah, I mean, our technique seems to me quite constrained to what we do. So I don't have a great intuition on your question.
And maybe there's some flows that are truly stochastic or something that you're not just relying on shear flows or something. Yeah.
That's another. I mean, if you try with a stochastic flow, that might be more flexible. Krachner model, or that would be a keyword, but good question.
Any more? If not, we thank the speaker again.